when it comes to these sorting machines, you said it's about adding some infusion to the either the cone or the pre-roll, correct? So
Yep.
up until your portion of this manufacturing, can you tell me a little bit about the steps that would happen prior to your portion at Sorting Robotics?
If you look at the, I guess, whole value chain of cannabis, we don't live at the end. The end you could kind of assume is like retail or delivery. And we don't really live at the very beginning. The beginning is, cultivation, or even before that, it's more like genetics and breeding, and then getting, either seeds or clones to then get cultivated. We're kind of somewhere in the front middle of it, where we are helping manufacturers create retail ready goods. And so if you look at the very beginning, it's going to be um, a farmer is going to get clones or seeds. They're going to grow those clones or seeds into full plants. Those full plants are going to become dried and cured. They'll probably become trimmed. And then from there, that biomass or that kind of finished flower product is going to either go get extracted, packaged, or manufactured into other goods, let's say pre-rolls. And so that's kind of where we come in. And so if you have some flour that you plan on making pre-rolls out of, the next step would be to uh, prep that material to be integrated into a pre-roll. And then you would manufacture the pre-roll, and that can be done either in like an automated fashion. There's some machines that, take a good attempt at manufacturing the pre-roll in an automated way. And then there's also some semi-manual ways of manufacturing the pre-rolls called knock boxes. And they're just basically like vibrating plates that knock the flour into a like kind of ready-made cone. And then once it goes through that phase, that's when it gets to us. And we have this kind of like small sliver of the value chain inside a small sliver of the market, which is pre-rolls. And we provide technologies for doing what can be considered the most difficult part of the pre-roll manufacturing step, which is the infusion of cannabis concentrate or cannabis material into a ready-made pre-roll. So ready-made pre-roll is like flour that's dried and you kind of pack it into a tube. So then how you enrich that pre-roll is very difficult to do by hand, and it's very inconsistent if you do it by hand. And so we come in and we make it easier, more consistent, and like kind of overall cheaper for the manufacturer to do it. So that's when we come in, and then we have our first machine, which is the GK robot, which injects cannabis pre-rolls with concentrate material. And that could be either like a concentrate of like an oil or a concentrate of like a wax. It's kind of heated up, and we kind of squeeze it into the center of a pre-roll. And that would be what's called like an internal infused pre-roll, where you have a pre-roll and now there's a bunch of concentrate on the inside. And then we have another machine called Stardust, which is a coating system. So that's an externally infused pre-roll. So you could take a pre-roll, and instead of shoving a bunch of stuff on the inside, you can coat the paper like how you kind of alluded to before, where you either put like cigar glue and then keef or cannabis powdered concentrate on the outside, or you spray it with cannabis oil and then cover it with that keef or what's called bubble hash, but more like type of powdery cannabis concentrate. And then that gives you an externally infused pre-roll. And then from then on, it'll go into like final packaging or maybe like final curing or quality control. And then it moves on down the value chain. There's no cannabis in our facility, right? This is like, it's just a building with a bunch of robots and engineers. So that's what we do. We just are, we provide like kind of picks and shovels for the industry as opposed to mining for gold.
What are the mechanical components involved in the automation of cannabis manufacturing systems like the ones at Sorting Robotics? Can you tell me a little bit about that?
Yeah, I mean, so in starting robotics, we have a pretty wide range of mechanical systems that are, application specific and sometimes a little bit more generalized. But we kind of have a standard tool suite of electromechanical devices like motors, microcontrollers. Stardust has a pretty robust industrial robotic arm, and some of our other systems have kind of very complicated heating algorithms and heating systems. And a lot of the process is mostly like heating, measuring, manipulating of objects. And we have like a family of technologies that we kind of reconfigure for different applications. All of our systems are technically robots, but I would say the most kind of outward perspective of a like robotic technology would be the robotic arm. And so in Stardust, we were tasked with designing a system that would coat the outside of a joint. And you can imagine that's a pretty vague, that's a pretty vague thing to do. So the robotic arm is probably the strongest piece of technology that we've had integrated into our systems because it gave a ton of reliability to alternative paths of manipulating the joints. So material manipulation is kind of the name of the game for any robotic system anywhere, right? Whether it's a humanoid robot that's picking up like firewood or whatever, or automotive parts in a manufacturing company, or it's our robotic arms integrated into our systems that are manipulating individual joints. You could make that same manipulation of the joint done with a kind of like roller coaster track system or something like that, but it would become very dirty. It'd be difficult to maintain. Contamination risk is a huge thing, and it would just become very complicated. And when it's very complicated, it can break down. There's just more things to break down. And in our situation, we were able to develop a system that has two moving parts as opposed to 200 moving parts. And it's basically just a robotic arm and the little end effector on the robotic arm. And then that's it.
So in the R&D process of that, choosing the end effectors that you were going to use, did you have like a trial and error process to figure out which end effectors were going to be best for this application?
Well, we designed our own end effector for this application because the
So,
problem was so complicated. But yeah,
so how many, like, how did that go? Tell me about that process. I mean, I know it's just one little end effector, but did you
yeah.
get it right on the first try? Or did you have to go through a couple iterations?
The end effector itself, we that was like one of the few things that we actually got right on the first try. Um, because the end effector itself is actually quite simple. It's basically a motor that spins a bunch of magnets. That being said, it is quite complicated. Or actually, no, it's maybe not complicated, it's more complex. There are like several parts to it that have to work together, but they're all driven by like one motor. The parts are all very simple. It's like bearings and gears, like things that are very well known. We didn't have to like invent anything. We even had them on a shelf somewhere and like, okay, well, like if we use those bearings from there and then these gears from there, and then like maybe this motor that we'll buy on, I think the first one we probably bought like on Amazon or something and then, took it out to something nicer. But uh yeah, that one was pretty straightforward. Now, how the end effector integrates with the rest of the system, and then how those things, that was a much more difficult problem because the end effector itself as a subsystem is quite simple
Tell
to
me
recognize.
about that. Tell me what the iteration process was on that, and
Oh man.
maybe the
Okay, yeah.
time frame and the late nights.
Yeah. So the okay, so this is actually kind of fun, right? So um there's a question that was in the design process, and the question is how do we put joints into the system and take them out of the system? Right? And you need to grab only the crutch of the joint because you don't want to kind of shadow any of the place that needs to get sprayed with material or anything. And then you also can't grab it too hard. You need to make sure that it's well aligned. You need to be able to control it, and you need to be able to clean whatever mechanism you use to grab it. So like a pretty difficult set of requirements, especially when coming from this like semi-rigid member, which is like a cannabis joint. We built this thing called a collet pod, which is a kind of like a cylinder that is a magnetically actuated collet that grabs onto the joints. And it's like kind of one of our biggest patents that we put onto the machine because there isn't that like that doesn't exist at the moment. Their collets are normally like screwed on, but we figured out a way to like magnetically actuate them. And so we said, okay, we designed this thing But then now how do we put joints in it and out of it? And then how do we then get that grab holder collet pod onto the end effector and like present it and take it away? And so that's where the big problem came into, because it's like how do you go through like a membrane, right? Like you're going through this plane where like inside the work cell, it's kind of like super dangerous. You got this thing whipping around, you're like spraying stuff. Like you don't want to have any exposure of that to the rest of the world. And you also want to interface from the rest of the world into this work cell. Our first go at it was like, okay, why don't we put little ridges around the collet pod and put ball detents to kind of like hold it into place. You kind of like pop it into place, and then the robotic arm will come with magnets, and it will just like both grab the collet pod and then magnetically actuate the collet pod to grab the joint. And then you'll just like pull it through the ball detents. That seemed like a pretty good solution. So that was our first cut. Kind of immediately after we developed it, we kind of noticed that there was a risk for people to like push it through the Baldy tents all the way, and then it would just like fall into the work cell, and then you have to like open the door and go into it. And so that was like, okay, maybe that's kind of a small risk. But then we noticed a much bigger problem, which was that the Baldy tents would get dirty and then they would stop working. And so we're like, oh God. And you have to keep in mind, right? Cannabis manufacturing is like a very dirty process. There's like dust and stuff everywhere. And so we said, oh God, how are we gonna fix this? And we thought of a bunch of ways on how to do this. This end effector, which is kind of looks like 10 magnets on a disc. The way we would come up to the collet pods was we would just like come up behind them, and then the magnets would like kind of snap the collet pods to the end effector, and then it would pull it out. But the way we would put back the collet pods is we place them back into the hole, get them onto the baldy tents, and then how do you take the magnets off the magnets of the end effector? Well, we just twisted it. And we twisted it to kind of get the magnet on the end effector away from the magnet of the collet pod, and then it would just release. And it was, it kind of worked pretty well. But then after doing that a few times and running into this like contamination issue, we thought of a much better idea, which ended up being like amazing, and it works. It works amazing. And what we ended up doing was we ended up actually integrating a floor. So took out the baldy tents, and then we had all the collet pods rest on a floor with a bunch of holes inside of it. And so then we would actually just use the rotation of the end effector to both activate the floor and then grab the collet pod. So if you can imagine this, imagine a disc, and then that disc has 10 different holes inside of it, but in between the holes, there's flat pieces. And so when the station is loaded, the flat pieces are under the little joint holders. And then when you want to come and grab the joint holders, you come up, you rotate the floor out of the way, so then all the joint holders snap to the end effector, and then you can pull them out. And then when you put them back, you just rotate back the floor, and then the floor is the one that kind of catches the collet pods as it releases from the end effector. And that was like a very clever sort of solution that we developed after a couple months of trying to figure it out and running into this issue, and then it solved a few problems, right? It solved the contamination problem, and it also solved the problem of the joints never fall through into the machine because there's a floor, so it can't go anywhere. And then it's also super easy to clean, and yeah, it was just that was cool. And then it also reduced the amount of moving parts and replacement parts. And yeah, simplicity was the key there. And utilizing every aspect of this robotic arm is what made it really, really significant. That's probably one of my favorite parts of the design.